So now our question is how we can actually build a filter. So in the right side you can see there is our circuit. Okay, and this is the RC circuit, simple RC circuit. Okay, so here we have the voltage, or we can say our signal, the signal that actually contain my 50 hertz, and there is my 500 hertz signal. So I am feeding this signal here in this network, so RC circuit, and I am taking the output from this capacitor side. Okay, from the capacitor portion I am taking my output. Okay, so if you remember, there is a term called reactance. Okay, I hope you remember the term is called reactance. Okay, reactance normally actually it is represented as uh, sorry, x. Okay, x, that is equals to, for a capacitor, that is 1 divided by 2 into pi into the frequency multiple by the capacitance. Okay, so I have a reactance, so the reactance is equals to 1 divided by twice pi fc. Okay, so the reactance of the capacitance is this. So what does it actually mean is that, so when I have a frequency, okay, if the frequency is getting higher, okay, if the frequency is getting higher, that means the xc, that is the reactance, will only get lower, right? Because it is inversely proportional. So if the frequency increases, the reactance decreases. In the oppositely, if the frequency decreases, the inductance, the reactance increases. So what it means actually, as the frequency is getting higher and higher, my reactance is actually getting lower and lower. So when this reactance, this portion reactance of this actually branch, if the reactance is very low, say Xa becomes 0. Okay, Xa becomes 0, that means it is now actually behaving like a short circuit. Okay, I don't have this anymore. Okay, let's actually do this like this way. So I don't have this capacitor branch anymore, rather I have this shorted side. Okay, so when my frequency is very high, my reactance is very low, so I have shorted, so my V output actually becomes 0, right? Okay, in the opposite scenario, when I have low frequency, this is no longer 0. Okay, this is no longer 0. I have a very good output, here. Okay, so that output, V output is equals to, this is a simple voltage divider branch. So I have V input multiple by, that is my Xc, okay, divided by Z, where Z is equals to actually, let's write it down, that is my square root of, okay, that is my R square, right? R square plus Xc square, that is my Xc square. Okay, so now if we actually try to plot a figure like this way, so this is my frequency. So as we saw that, and this is my V output. Okay, this is my V output. As the frequency was getting higher, my V output was getting lower and lower, going towards 0. Okay, and when I have very low frequency, I have very high output, because Xc is low frequency, Xc is very high, so it is proportional. So X is proportional to my V output, so I have very high. So I have a figure, I will get a figure like this, a slope and this curve, this flattened curve. So at low frequency I have very high amount of output, at high frequency I have a very low amount of output. So this actually quite kind of looks like a low pass filter, right? So if I actually implement this one like this way, I have very high output, then I have very low output. Okay, like this. So if this is my output, so anything outside this portion, so this portion is getting cut out. Okay, I don't have any output here, anything here is actually cut out. High frequency components, anything that was here, high frequency component, that is no longer here. So this is cut out, I only have this portion, so I have a low pass filter, right? So a low pass filter can be designed by a very simple RC circuit, where we're taking the output from the capacitor side. Okay, from the terminal of the capacitor, we are taking the output. Now one thing that is important is that what is that, there is this portion, we call it a 3 decibel point. Okay, 3 decibel, 3 decibel, actually this is my 0 decibel, this is minus 3 decibel, which is actually equals to 70.7%. okay, around 70% of my this primary value. This is like this portion, this is the frequency here. This is what we call my cutoff frequency, right? Okay, so this is 70% of my initial value, but the highest value, that is my cutoff frequency. So only one thing, so this was my 50 hertz, right? This was my 50 hertz and this was my 500. Okay, so I have to, okay, have a cutoff frequency in between somewhere here. Okay, in between somewhere here I have to have a cutoff frequency, because if I build a circuit like this way, okay, like this, so cutoff frequency is like 101 kilohertz, then it is not going to actually suppress this portion. So I have to have a cutoff frequency which is greater than 50 hertz but less than 500 hertz. Now that is the question. Our next question is how to get that cutoff frequency. Okay, so that's what we are going to answer now. So let's of these portions out. I don't need this ones. Okay, so now fc, that is my cutoff frequency, that is equals to again 1 divided by, okay, that is actually 1 divided by 2 pi rc, 2 into pi into 2 into pi into r into c. So my cutoff frequency actually depends on the value of r and c. This is the r and this is the c, the capacitor. So the value of resistor that we are using and the value of capacitor that we are using, that determines my cutoff frequency. So say if I use r is equals to, like, say for example I use 10 kilo ohm. Okay, 10 kilo ohm, and I say use a capacitor of say 1 microfarad. Okay, 1 microfarad. So I can calculate my cutoff frequency from that. So yeah, if you calculate this cutoff frequency, it will be like around 15 hertz. Okay, so around 15 hertz. So try that. Okay, if I actually made any mistake, so 15 hertz. Now, so changing this value, I can actually design my filter, that is my low pass filter, to have a particular cutoff frequency. Okay, so I hope this is clear to you. So let's actually go back and try to build this one in PSpice. Okay, so you have to do this, so try to do this now. So go to project, so I go to project and let's make it name is as LPF1. okay, and create a blank project. Okay, so like this. Okay, now what I want here, I strict it somehow like this. Okay, so go here and take VSC. Okay, that will be my input wave signal. Okay, I need one resistor R, that gives me the resistor, and I need another capacitor, that is my C, that it gives my capacitor, and click R and it will automatically rotate. So, and I need my ground. Okay, I have my ground, so I have my all components. Now let's just connect this. Okay, let's just connect it here like this, then connect it. Okay, so I have my all the components. So I have 1 kilohertz frequency and 1 nanofarad. So I want to change this value. Okay, let's change this. No, not this. So let's make it 0.01 microfarad. Okay, 0.01 micro. You will go for micro, and I have 1 volt AC. Okay, let's make it a little bit. Let's make it 10 volt AC. Oh, okay, 1 volt is okay. So 1 volt AC. So I want to place, this is my input probe and this is my output port. I am taking the output across the capacitor. So across the capacitor, that means capacitor to ground. Okay, so let's create my simulation. Low pass filter 1. Okay, here now I don't want time domain simulation. Now I want AC sweep. Okay, AC sweep, here you can see. So when you choose AC sweep, there is sweep type, linear and logarithmic. I will choose logarithmic. So we want to see the output from frequency. Start frequency, let's make it 1 hertz and make it 100,000, or no, 1 million. Make it 1 million. Okay, and make the points per decade as 10. So apply it and click it. Okay, so I think everything is okay. So let's run this one. Okay, let's see the output. So you can see the green one was my initial input signal, that was my 1 volt, and this is my output signal 1 megahertz, up to 1 megahertz. So you can see it is actually cutting out in this portion like this way. Okay, so you can see my like I said 70%, like 70%. So this is my 70%. If you look at this frequency, it will be like around 15 or 16 kilohertz. That was the cutoff frequency that we get with that value of resistor or capacitor that we used. Okay, so this will actually allow this portion to pass, and it is actually cutting out any output. This was my input signal, and from the output side, in the output side, I am not getting this one. I am getting only this portion. Okay, so this is actually acting as my low pass filter. One other thing that you need to notice here is that this slope we have, okay, and this is not a like a sharp cutoff. I am not getting a sharp cutoff here, rather I am getting a gradual cutoff. Okay, so let's go here again. So this is what I'm saying, that I am actually getting a gradual cutoff. Okay, gradual cutoff. I'm not getting a sharp cutoff. So now that is actually a problem. Problem is because say when I have a very in this side, when I have like the very close frequency range like 550, so if I get a gradual cutoff like this way, so sometimes I will get a portion of 500 hertz also, but I don't want any frequency signal of 500 hertz. So I need to have a very sharp cutoff so that I don't get any 500 hertz. So I have to actually straighten my curve. Okay, and how to do that, that will be our next question. So another thing is that, so and this is what we call this slope we have, we call it 20 decibel per decade. Okay, this slope, and this slope is actually like 20 dB, you know, dB per decade. Okay, 20 decibel per decade, or it is also called like 6 dB per octave. Well, 20 dB per decade means per decade it is actually decaying by 20 decibel. Okay, so it is actually decaying per decade, it is decaying by 20 decibel. Okay, so another thing is that you should notice that here when I have the cutoff frequency, my actual value, my original value has somewhat decreased. Okay, I do not have my input value. The amplitude of my output signal is quite attenuated. Okay, and that is another problem. Okay,